Well, this is part 3 of a series on playing with the RYLR998 LoRa transceiver from RYLR998. By the way, I've put a correction in the description for part 1 where I falsely say that the baud rate of the 998 cannot be lowered to, say, 9600, which the Arduino Uno's software serial capability could handle more reliably. But I'd already committed to using the extra hardware serial port of an Adafruit Itsy Bitsy M0 Express, which I've already acquired and which I wanted for other reasons too. It's a small size and its capability of storing software and its 3.3 volt logic. So I will not be further exploring the Arduino Uno's capabilities. We're testing my first attempt to program a repeater capability into these Itsy Bitsy M0 Express microcontrollers, which are teamed up with these little LoRa transceiver modules from from RYLR998, the RYLR998s. This is node number 1, which is going to be originating a message here from the serial monitor here of the Arduino sketch that's controlling it. The message is testing 1, 2, 3, and I've prefaced the message with an @to 1. Any message that is prefaced with an @to is intended to be sent by the repeater to the address following the word to. And so in this case, back to number 1. I only have 2 of these microcontrollers at the present time, so to test the repeating capability in node number 2, I have to have it send the message back to itself. So here's the repeater, here's node number 2, which is programmed to be a little repeater. Okay, and we'll see how this works. We'll send this message via node number 1 to node number 2, the repeater. Hopefully it will be received, and then we've got something back here. Okay, here's what happened at the repeater. It received a message from node number 1. That's at the top there. Receive equals 1, an 18-character message, to which it then appended a -20 for the received signal strength indication, and an 11, which is the signal-to-noise ratio. Pretty good. It's 11 dB over the noise level. Okay. Then it sent a message back to node number 1, which is now longer. It's 25 characters long. And notice that there's some additional stuff on the end that we're going to see over here. We're now counting the original -20 and 11 as part of the message, and so it's longer. But we're also tacking on an additional RSSI value of -19 and 11 because that's being tacked on by the receiver over here. When it received the message back from the repeater, it gave its own appraisal of the received signal strength and its own signal-to-noise ratio. Okay, well, I don't think we need double RSSI and signal-to-noise ratio values, so I'm going to have to trim that off of the end here. But the basic repeater functionality is working at this point. Well, the additional Itsy Bitsy has arrived, along with a solar panel, a solar charge controller, and a battery. I have 28 header pins to solder onto the Itsy Bitsy. I like to push the headers into a breadboard, place the board onto the pins, and secure it with a rubber band, and then go from there. Well, here I've soldered the 4 corners of the header pins onto the Itsy Bitsy. Next we'll remove the rubber band and continue. Well, once the rubber band is removed, I finish soldering the remaining 24 pins, then inspect the joints with a magnifying glass for unwanted solder bridges between pins and for cold solder joints. The cold solder joints would typically look like a sphere sitting on top of the uh, circuit board. Good solder joints look more like cones, truncated cones with the top at the top of the pin and widening as they approach the printed circuit board. And even though some of these look like spherical globs in this picture, closer inspection with a magnifying glass showed that all of the joints were good. They were inspected and passed. I also soldered headers onto a solar charge controller board from Adafruit. It's at the top of the breadboard seen here. And I added an on-off switch that shuts off 5-volt power from the charge controller to the Itsy Bitsy while allowing charging of the battery either from the solar panel or anything you connect to the charging controller board by a USB-C connection. Could be a laptop or a portable cell phone charging battery. So the whole test setup for the outdoor repeater is shown here. We'll see if enough solar energy makes it through the plastic container and generates enough power from the solar panel to keep the battery charged. Well, testing the repeater, I'm about to send a 115 character message to another node via the repeater. It's a 115 character message because that's the length of message I've found is reliably transmitted from one node to another. I'm not sure why it begins to generate checksum errors at longer lengths, but I'm going to stick with 115 characters now while I get this repeater set up going. And here we see that the 115 character message was received in another room with no errors in the characters, and it was actually received. Notice that there is now only one set of received signal strength and signal to noise ratio values tacked onto the end of the message, which was a goal still in the part two. So what's next? Well, to make this into more of a genuine wireless hub and spoke network, something has to control who transmits when. And my current thought is that I need the repeater at the hub to control that. My thought is to make it beacon a clock signal to all the nodes on the network. Then each node will be assigned a separate transmit time, and it will not be allowed to transmit at any other time. And this will be signaled, as I'm conceiving it now, by the dot star LED on each node's Itsy Bitsy, telling the user that it's okay to transmit now. We'll see how that works, and maybe also find out about how the solar panel performs encased in plastic next time in part 4.